All right, today we're looking at four complex numbers. So I have some bad news to start. All right, your teachers up to this point have all been liars. Okay, if you can think back to elementary school and even middle school, if you were told something like the square root of -4, even if you typed it in your calculator right now, what would happen is this error, or not, sorry, not that error. You just get an error on your calculator, okay? And your teacher said, you can't do this operation. It does not work. Well, turns out they were lying, all right? And that's what we're gonna learn today. So first things first, the answer to that is just not a real number, okay? The answer does exist. It's just part of what's known as the imaginary set of numbers. All right. So first things first, when finding the square root of a property of, or square root of 4, provides us with an answer of 2 or -2. And if you think about that, 2 times 2 is 4. -2 times -2 is also negative or 4. All right. It says we reach an impasse when we try to find the square root of a negative number. And that's kind of what we were getting at before. Teachers up to this point told you it does not work, it does not exist. Well, mathematicians, as smart as they are, discovered what's called the imaginary unit. All right. And this is super important to kind of understand and comprehend that the imaginary unit is defined as the square root of -1. All right. If we can let our understanding grasp this concept, grasp this idea, all right, all of the math we've done makes sense. I just realized the screen is on our other stuff. Not that you're probably looking at that anyways, but hi. All right. If we can let our minds take this in and account for this, and allow imaginary numbers to exist, the math continues to make sense. All right. So when we're simplifying radicals, keep in mind, we can always break them apart into a product of two numbers. So I could say the square root of -1 and the square root of 36. That's the same thing as the square root of 36. At this stage, then I can break it up into the square root of -1 times the square root of 36 using my properties of roots. Square root of 36 is 6. Square root of -1 is I, which means the square root of -36 is 6I. All right. Using that same mentality, we can simplify the square root of -75. So I'm going to break it up into -1. Perfect square factors of 75 are 25. 3 is not, but this will help me break it down. So we have the square root of -1, square root of 25, and the square root of 3, which means we have 5I times the square root of 3 is the square root of -75. Okay. Reason this is so important is up to this point, we kind of hit a dead end. When we have the square root of a negative number, it just error. It doesn't work, okay? But again, if we introduce this idea of imaginary units, and we can, all of the math continues to make sense, okay? So what we just found are purely imaginary numbers, right? Purely imaginary numbers are in a subset of complex numbers. If you kind of remember back to chapter 1, we had real numbers, and then we had complex numbers. And then within real numbers, this is kind of what you've talked about up to this point. We have, rational and irrational numbers. And then within rational numbers, we have, integers and whole numbers and natural numbers, and goes from there. But complex numbers is this big set. And here we have imaginary numbers, if you can kind of think of that. All right. So we have real and we have imaginary numbers. If we put them together, they're in the set of complex complex numbers. And again, that's back to, I think section 1.1 or 1.2, if you want to go back to the notes and kind of look that over. All right. But today, we're going to be delving into properties and operations with complex numbers. So kind of the first thing, just like before, everything in math holds true. So when I see a problem like this, you can almost treat the imaginary unit like an x. So now I have negative 4i times 5i. I wind up with negative 20i squared. The most important thing about today is whenever you see an I squared, that always equals negative 1. So you will never have an I squared in your answer. And as we write the answer down here of 20, I just want you to kind of take that and, you know, let that soak in, if you will. So we just multiplied two purely imaginary numbers, okay? We can't, there's nothing tangible that goes with them. But we multiplied two imaginary numbers together and got a real number. So essentially we took something, or we made something out of nothing. Isn't that exciting? Super cool to do in math. All right, next question here. Again, we want to break these down. Negative 16, that's already a perfect square. So hopefully you can kind of see the square root of negative 16 is 4i. Negative 20 is negative 1, 4, and 5. So this one is 2i square root of 5. And then when I multiply those together, I get 8i squared, square root of 5. You'll notice that I always write the I in front of the root, and that's just to kind of help with your notation. Again, no I squareds in our answer. We wind up with negative 8 root 5. So again, we took two imaginary numbers, we multiplied them together, and somehow they magically equal a real number. All right. Last one here, same idea as before. You can break these up any way you want. You can put them together if you want. I'm actually just going to leave them separate for now. So we have negative 1 and 16 and 3 gives me 48. We have negative 1 and 25, 16 and 5. All right, so kind of looking at this problem here, we have 4i square root of 3 over the square root of 5. And then this one, square root of 25 is 5. Square root of negative 1 is I over 4. So we wind up with 20i squared, square root of 3 over 4 root 5. Remember again, no I squareds in your answer. So we wind up with negative 20 square root of 3 over 16 root 5. You can reduce 5 over 4. And then hopefully you recall in math, we don't like to leave radicals in our denominator. So we're going to rationalize. We're going to multiply the top and bottom by the square root of 5. And we're going to wind up with what do they do here? Just checking. Oh, whoops. Right back here. I don't know why I did that. That should be a 4, which means I didn't have to reduce that. My apologies. Negative 20 over 4 is going to be 5 up there, and that 4 drops out. Sorry, that wasn't a 16. I don't know why I wrote 16. But we have negative 5 root 15 over square root of 5 times the square root of 5 is 5, which means I have the negative square root of 15. My apologies there. I don't know why I wrote 16. That was my mistake. All right. So those are some basic operations with imaginary numbers. The nice thing about this is that's going to help us eventually solve quadratic equations where there was no solution. i.e. a situation like this, okay? With quadratic equations, we know there's two solutions. They just might not necessarily be real solutions, all right? So like in this situation, do our algebra just as we know how to do. Then we divide by 4. We wind up with x squared equals -9. And we're going to square root from there, which means x equals plus or minus 3i. All right. So again, if we allow our understanding of math to include the imaginary unit, we do everything the exact same as we've been doing. Second part of the day is looking at more operations with complex numbers. So numbers that have a real and imaginary component, not just imaginary components. Again, here's that chart I was talking about before. You have the set of complex numbers which contain real and imaginary components. You also have purely imaginary numbers. All right. Looking at this first example, we want to make these two the same. If you notice, this is your real component and this is your imaginary component. All right. So we have one complex number on the left. We want it to equal the complex number on the right. All right. If we want two complex numbers to equal each other, well, the real components would have to be the same. All right. Additionally, our imaginary components would have to be the same. And then we can solve from here. We wind up with 3x equals 9, which means x is 3. And over here, we subtract 2y. We wind up with y is 1. Again, if you want to make sure or equate two complex numbers, you need to make sure the real components are the same, and you need to make sure the imaginary components are the same. All right. The final thing today, I know it's been a lot, but all we're going to look at is adding, subtracting, multiplying, and dividing complex numbers. These are actually very straightforward for you, all right? And your intuition would kind of lead you down the right path. So if I'm adding two complex numbers, what do you suppose you do? Oh my gosh, you are correct. We want to combine the real components, and we want to combine the imaginary components. Subtracting, same deal. The only catch is we need to be mindful of that subtraction. So we have 5 minus a -2 as a real component, which is 7. Then we have -11 minus 4, which is -15i. And that's my solution when subtracting. So adding and subtracting, keep the reals together, keep the imaginaries together, and just basically essentially combine like terms. When we are multiplying, you guessed it, we need to FOIL these expressions. So we're going to wind up with 18 plus 12i minus 12i minus 8i squared. In this instance, it looks like our i's will cancel. We know I squared is in fact -1, so -8 times -1 is +8. 18 plus 8 is 26. Again, here's another situation where we take two complex numbers with imaginary components, we multiply them together, and they equal a real number. If you are interested in electrical engineering, this is one place where complex numbers are used all the time, okay? So something to kind of look forward to if you are indeed going down that field and path, all right? The next problem we're looking at is division of complex numbers. Well, this is where we kind of hit a bump in the road, because if I asked you to cut your pumpkin pie next week into, 3 minus 2i pieces, you would look at me like I was crazy and send me to, wherever, all right? Dividing by something that doesn't exist is really hard to do, all right? It doesn't make sense. So the question is there a way that I could switch this around and divide it by something that is real? Well, in fact, there is an operation that works. And just kind of like looking at C, if we multiply two numbers together, sometimes we're able to yield a real result, okay? When we're dividing by a complex number, the trick is to multiply by what's called its conjugate, okay? So we take our denominator and all we do is we flip the sign on the imaginary component, okay? If we do something to the bottom in math, we also have to do it to the top, because essentially what I'm doing is I'm multiplying the fraction by 1. When I multiply by 1, it doesn't change the value of the answer, it just changes how it looks. At this stage, we can then FOIL out the top and FOIL out the bottom. So we wind up with 3 plus 6i plus 2i plus 4i squared. On the bottom, we have 9 minus 6i plus 6i minus 4i squared. Remember from before, I squareds are -1. Notice those cancel in our denominator. In our numerator, we have 3 minus 4, which is -1. 6 plus 2 is 8i. And then 9 plus 4 is 13. At this stage, I would encourage you guys to write the complex number in standard form, where your real and imaginary component are written separately. All right. So at this stage, again, we multiplied the top and bottom by the conjugate. We were able to get a real number in my denominator. And now I can divide something by 13. That operation makes sense. That's a tangible number. I can divide both the real and imaginary component by 13. This original fraction is equivalent to this one. It's just we're not dividing by an imaginary number anymore. All right. So those are the operations with complex numbers. Your homework's on the bottom. Let me know if you have any questions on this. We're going to spend a few days on review when you get back from break. And then your quiz will be Thursday following this break. So if you have questions, feel free to ask via Google Meet or discussion board. But best of luck. Hopefully these make sense. Let me know if you have any questions. Great seeing you. Enjoy your few days off.